Now the next question that we have is, a DC series motor fed from rated supply voltage is overloaded and its magnetic circuit is saturated. The torque speed characteristics of this motor will approximately be represented by which curve? So for a DC series motor, the speed torque characteristics will resemble C, right? But now in this question, what is given extra is the DC series motor is overloaded and so its magnetic circuit is saturated. So what does saturation of magnetic circuit mean? It means that it will no more respond to the changes in the field current. Usually the flux will be proportional to the current that is flowing in the coil, right? But if it is saturated, it means that there can no more be any magnetic circuit that can be increased even if there is an increase in the current. So for the series motor, the field current, the armature current and the supply current, they are all one and the same. Okay. So if you take the expression for speed, omega is equal to the back EMF divided by K into phi. So these both are constant, they are not changing. So this is equal to EB is the supply voltage or the terminal voltage VT minus the drop across armature and series winding. So IA into RA plus RSC, just like we did when we were deriving the characteristics, right, divided by K phi. Now what is the torque? We know torque is related to the armature current as K phi IA. Okay. So now remember, even though this is a series motor, this K phi is remaining constant. So essentially this is becoming the same as a shunt motor. So that means the characteristics will be similar to that of shunt motor. So that means B. But we will see through the equations as well if this is really coming out to be the case. Okay. So then omega will become Vt by K phi minus Ia you can write as T by K phi. So T by K phi whole square into Ra plus Rse. So now this is a constant. This entire thing apart from T is constant. So it is a equation of a line. So it should be the curve B. The next question we have, a DC series motor driving an electric train faces a constant power load. It is running at rated speed and rated voltage. If the speed has to be brought down to 0.25 per unit, the supply voltage has to be approximately dash. Okay. So how do you solve this? This is in per unit. Okay. So how do you solve this? First information, as always, it is a series motor. So first draw the circuit diagram for series motor. Next, what else is given? It is running at rated speed and rated voltage. Whenever we are dealing with the per unit, the rated values we will take as the base values, so that they will become, in per unit, they will become 1 per unit. Okay. So speed is equal to 1 per unit because it is the rated value, and the voltage also you take as 1 per unit since it is the rated value. Okay. Now what else is given? If the speed has to be brought down to 0.25 per unit, so we will take this as omega 1. This is the first case, and the voltage also we will take as V1. Now what do we want? We want case 2, this is case 1, and case 2, the speed omega 2 is 0.25 per unit, and we want the value of V2. So this is the voltage V1 and V2 we are talking about. Okay. Another important information that we have is the load is a constant power load. So what is meant by constant power? P is equal to the back EMF into the armature current. This is staying constant in both cases. Okay, same in both cases. So using this information, now we have to find out V2. Now since no other parameters are given and the armature resistance is also not mentioned, we can take the armature drop to be negligible, and also here you have has to be approximately. So that means there will be some approximation. Okay. So ignoring the armature drop, we can equate the back EMF to the supply voltage. That means whatever voltage is given, that will be the back EMF. So from here what will you get? V1 will be equal to back EMF, you can write as K phi omega 1. Now the flux is directly proportional to the armature current. This is a series motor. So you will write K into some Kf constant into armature current into omega 1. This is one equation, let us say. Now similarly we can write V2. Similarly V2 is equal to K phi omega 2, which you can write as K into Kf into Ia into omega 2. This is the second equation. Now this constant power condition, if you take V1 Ia1 is equal to, you can write armature current 1, armature current 2 here. So V1 Ia1 is equal to V2 Ia2 because P is equal to constant. So from here you are going to get V1 by V2 is equal to Ia2 by Ia1. Now Ia2 expression from equation 2 you can get, what is it? V2 divided by K into Kf into omega 2 divided by Ia1. Similarly it will be V1 by K Kf into omega 1. So from here you are going to get V1 by V2 whole square is equal to omega 1 by omega 2. V1 is given as already 1 per unit. So 1 by V2 square is equal to omega 1 is 1 per unit, omega 2 is 0.25 per unit. Okay. So from here you are going to get V2 is equal to 0.5 per unit. Okay. Approximately 0.5 per unit. The next question we have, a 50 kilowatt DC shunt motor is loaded to draw rated armature current at any given speed. When driven at half the rated speed by armature voltage control and at 1.5 times the rated speed by field control, what are the output powers delivered by the motor in each of the cases? So like always, you will first start with writing down whatever information is given, right? So what is the first information? It is a shunt motor. So you will draw the circuit diagram. Now what is the rating that is given? It is given as 50 kilowatts. So this will be the output power that it is delivering. Now what else is given? It is loaded to draw rated armature current at any given speed. That means the armature current is going to be constant with respect to speed. Okay. Now when driven at half the rated speed by armature voltage control. So in case 1, the speed control that is being used is armature voltage control. And in this case what is happening? The speed will be half the rated speed. So we will take omega r to be the rated speed. And in the second case what is happening? Field control is happening. Speed is being controlled by controlling the field. And this case the speed is 1.5 times the rated speed. Now the question is, what are the output powers in each of the cases? We know the expression for output power. It is given by EB into IA. Now what is the expression for EB? It is K phi into omega into IA. Now since the rated output power is given by 50 kilowatt, okay, that means at rated speed and rated armature current you are going to get the rated output. So you can write 50,000 watts is equal to K phi into rated speed into rated armature current, where omega r and IAR are rated values. Okay, so this is the units, watts. Okay, so 50,000 you can write. So this you can take as one equation. Now in case 1, if you see, in the armature voltage control, the power is once again EB into IA. This is equal to K phi into omega into IA. Now here the speed control method is the armature voltage control. So that means the armature voltage control is the voltage that is given to the armature circuit. Okay. So this is varying in armature voltage control. So in this expression you can write, instead of K phi, you can write using equation 1, 50,000 divided by the rated speed into rated armature current into omega is given as half the rated speed, so omega r by 2, into the armature current is given as, it is taking rated armature current only at any given speed. It is given in the question. It is drawing rated armature current at any given speed. Okay. So this is going to come out to be 25 kilowatt. Omega r and IAR will be cancelled. Now, what is the second case? The second case is field control method. That means phi is not constant anymore. But what will be constant? The back EMF. This is constant. So why is that? EB is given by the terminal voltage or the supply voltage minus the armature drop. Now the armature current is not changing with respect to speed, and VT is not changing because this is not armature voltage control. So the back EMF will be constant. Okay. So if you consider the back EMF at rated condition, then this will be equal to K into field flux, rated field flux into the rated speed. Next, EB2 is in this case 2. This will be equal to K into phi dash into what is the speed that is given? It is 1.5 times the rated speed. Okay. So equating both of these, what you are going to get? Phi dash is equal to phi r by 1.5. So what will be the output power? Output power is equal to EB2 into IAR will remain as it is. So EB2 is given by K into phi dash into omega into IAR. Now you substitute, instead of phi dash, phi r by 1.5 into omega is 1.5 omega r into IAR. So this is equal to same 50 kilowatts. Okay, there will be no change. Now another easy way in which you can get this direct answer is what? We know that the field control is a constant power control. Okay, in armature voltage control, torque will be constant. So this is a concept we have already discussed. So in that way also, since the power doesn't change in field control, it will remain at 50 kilowatts. You don't have to do all of this calculation. Okay. The next question, we have a separately excited DC motor runs at 1500 RPM under no load with 200 volt applied to the armature. The field voltage is maintained at its rated value. The speed of the motor when it delivers a torque of 5 Newton meter is 1400 RPM as shown in figure. For the motor to deliver a torque of 2.5 Newton meter at 1400 RPM, the armature voltage to be applied is dash. Okay. So this seems like a big question, but it is not that difficult. Okay. So what is the kind of motor we have? It is a separately excited motor. So first you will draw the circuit. This is the armature. It is given a supply voltage Vs, and this is the field winding, which is separately excited. Now it runs at 1500 RPM under no load, okay, with 200 volt applied to armature. So this you can take it as case 1, which is the no load condition. No load means it is not drawing any current. So the armature current is 0. The voltage applied is 200 volt. And the given speed is, it is in RPM. So we will take N. This is 1500 RPM. Okay. Next, case 2. Next information that we have is the field voltage is maintained constant. So you can take 5. Okay. Mention 5. Now the speed of the motor when it delivers a torque of 5 Newton meter is 1400 RPM. So that means now the current is changing. It is not 0. It is a loaded condition, but we don't know the value of current. What do we know instead? We know the torque. It is given as 5 Newton meter. What about the speed? Speed is 1400 RPM. Vs and phi are remaining same. Case 1 and 2, Vs and phi are same. Now what do we want? For the motor to deliver torque of 2.5 Newton 1 Newton meter at same speed of 1400 rpm. What should be the armature voltage? So in case 3, Vs is not same as case 1 and 2 anymore. Okay. So here what is the condition? T torque is 2.5 Newton meter, speed is 1400 rpm, and we have to find out Vs. Now what about phi? This is same. In all 3 cases the flux phi is same. So when 3 cases are given, it means that from cases 1 and 2 we get some information and we use that in case 3 to find out the missing parameter. Okay. So what is Vs here? Supply voltage we can write as the back EMF plus the armature drop. So all 3 parameters we do not know here, but the back EMF we can express in terms of the flux and speed. So for each of the cases we will use the subscript. That means the speed N1, in case 2 T2 N2, in case 3 T3 N3. Okay. So now what is the expression for EB3? This is equal to K phi into, we will use the speed in radian per second because the same K phi you can use for torque as well. Okay. So now we have K phi is a constant which is not known. Omega 3 is 2 pi N3 by 60. So you have to find K phi. You can find it from case 1. So that is because the back EMF in case 1 it will be equal to the supply voltage because the armature current is 0. So there will be no armature drop. So you can write from case 1 the no load back EMF is equal to the supply voltage which is equal to 200 volt, and also EBNL is equal to K phi into omega 1. So this is going to be 200 is equal to K phi into 2 pi into 1500 divided by 60. Okay. So if you calculate this K phi, you're going to get around 1.273. So now you can find the back EMF. What about the current? Now the current IA3 will be equal to T3 by K phi. So T3 is known as 2.5, K phi is also known. So this also you can find out. What else is left out? The armature resistance. So this you will have to make use of case 2. So once again from case 2, what information we have? We have the torque and speed, and Vs is 200 volt. Okay. So now EB2 which is equal to Vs minus Ia2 into Ra. Ia2 you can find out, right? So this will be 200 minus Ia2 is the torque T2 divided by K phi into Ra. And how will you find EB2? EB2 you can find out as K phi into 2 pi N2 by 60. Okay. So this will be 1.273 into 2 pi into 1400 by 60 is equal to 200 minus 5 divided by 1.273 into Ra. Okay. So here if you solve for Ra, you're going to get 3.4 ohms. So now you know all 3 parameters. You can finally find out the supply voltage Vs3. Okay. So this is going to be equal to EB3. How much will it be? 1.273 into 2 pi into 1400 divided by 60. This will be same as whatever you got in case 2 because it is the same speed and same flux. So it is going to be 186.63 volt. And Ia3 is going to be 2.5 divided by 1.273, which will be 1.96 amperes. So Vs3 you can write as 186.63 plus 1.96 into 3.4. So you're going to get 193.3 volts approximately.